We spent the last several days talking about net force, the sum of the forces, the total of the forces. On Friday, we briefly went and took a look at a couple of individual forces that make up the net force or the total force. Specifically, we talked about weight and the normal force, and a little bit about friction as well. You guys remember what weight means? W-E-I-G-H-T? As opposed to mass. There's your hint. Not mass, but weight. Yeah? Yeah. Mass is the amount of matter that something possesses. It's simply dependent upon the number of atoms, essentially, that are in my body or that are in the object. My mass will be the same if I go to Mars as it is on Earth, because the number of atoms in my body would still be the same. My mass doesn't change depending upon my position on Earth or depending on my position anywhere in the universe. My weight, however, does, because weight was defined as the force of gravity that acts on something. Now, the force of gravity depends upon the acceleration due to gravity, which varies. Here, where we are, it's about 9.81 meters per second squared, give or take a little bit. If we go to the top of Mount Everest, it's actually going to be a little bit less. So your weight will be a little bit less at the top of Mount Everest. If you go to a place like New Orleans or just about anywhere in Louisiana where it's actually below sea level, gravity would be 9.82, 9.83, a little bit more than 9.81. Which means you're going to be a little bit heavier there, weight-wise. Not mass, but your weight will be a little bit greater. We can find the value of weight, or the force of gravity, by multiplying m times a. The value of a would be, on average, 9.81. Because it's a specific number, we often write it as g. M, your mass, times g being 9.81. Really, it's still m times a, but we're just calling a g, since when we find weight, it's always involving the 9.81 meters per second squared value. Now, strictly speaking, it should be a negative value, but when we're talking about weight, we usually call it positive, right? Nobody says, when somebody asks you how much you weigh, nobody says, oh, I weigh negative 150. You weigh 150, right? Even though technically that force of gravity is downwards. And we just usually take the absolute value. Now, we talked about normal force as well on Friday. We said normal force is the force of the ground. Put that in quotation marks. The force of the ground pushing up at 90 degrees. There's a reason why we put ground and up in quotation marks, but we didn't put 90 degrees in quotation marks. The normal force, when I'm standing here right now, is the force of the ground. Okay, but for Adam right now, the normal force is provided on him by the force of the seat. The seat is pushing up on him. If I'm in a roller coaster, then it would be the force of the seat pushing up on me from the cart, right? The normal force provided on the cart would be by the track. The track would push up on it. So it's not always the ground, but we say ground because it's usually ends up being the ground. Why do we say up? Well, because it's usually up. Right now it's acting up on me. It's acting up on Adam as well. But if you happen to be in a roller coaster where you're on the side like this, the track actually pushes inward like this. The normal force will be horizontal instead of upwards. If you happen to be, how many people have ever been on a roller coaster that's gone upside down? All right, if you're in an upside down roller coaster, the normal force provided by the track would actually be down. See, it's usually up, but sometimes it's horizontal or sometimes it's even downwards. But it's always at 90 degrees. Even when it's horizontal like this, or downwards like this, or at an angle like this, it's always 90 degrees to the surface. This normal force is your apparent weight. This is how heavy you feel. Remember we said on Friday that your weight is how heavy you are. Your normal force is how heavy you feel. When I'm in an elevator and I feel heavier than I really am because it's accelerating upwards, I'm not really heavier. I'm still m times g weight. But I feel heavier because the force of the elevator floor is pushing up on me harder than gravity is. If I'm in an elevator where the cable breaks and I free fall, then my weight hasn't changed, but my apparent weight will. I'll perceive my weight to be zero because there's no normal force acting up. And that's when I'm floating around inside that elevator compartment as it plummets to the ground. So weight is how heavy you really are. in newtons because it's a force. Normal force is how heavy you feel in newtons because it's a force. Friction, on the other hand, and we'll spend quite a bit more time talking about friction today, but generally we would say friction is a resistive force. It resists motion. It doesn't mean that it slows something down. It usually does, but not always. If you slam on the brakes of your car and you skid, then that friction force is resisting motion and slowing you down. But if you put your foot on the gas pedal on ice, it's the lack of friction, the lack of resistive force that keeps you from moving. Right? When you put your foot on the gas pedal when you're on pavement, the friction force between the pavement and the wheel, or between the pavement and the tire, allows you to be propelled forward. So the fact that the wheel doesn't spin on the pavement, that it doesn't skid on the pavement, the lack of motion, the resisting of motion between the tire and the road is what actually makes, ironically, it makes you go forward. So the resisting of motion is what actually causes motion there. Now, we're going to talk, as I say, a lot more about friction today. In fact, we're going to classify friction as one of two types. There's static friction. Force of static friction is the force of friction that prevents an object from beginning to move. That would be this desk right now that you see in front of me. It's not moving right now. We know by Newton's first law, it's not going to ever move until acted upon by an unbalanced or a net force. But watch what happens. Just drop your pens for a second. I'll give you a chance to write this down. Watch what happens when I give it just a light push. A push of maybe 5 newtons. Desk isn't moving. The force of static friction is preventing it from beginning to move. This is kind of a wacky force. Okay, this force of static friction is a wacky force. In fact, I sometimes call the force of static friction my stubborn force. Static friction, stubborn force. And the reason I call it my stubborn force is because it's just that pain in the butt force that just wants to get to you. I push with a force of 5 newtons, and static friction pushes with a force of 5 newtons the other way. Oh, okay, I'll push with a force of 10 newtons then. What does static friction do? It pushes with 10 newtons the other way. Okay, I'll push with 20 newtons. Static friction pushes with 20 newtons the other way. It's like it's got a mind of its own, and it's trying to tick you off. However hard I push, it pushes the other way. It's stubborn. It's static. It's stubborn. It does what it needs to do until, you know what, at some point it just gives up. At some point it just says, oh, I can't beat this guy. He keeps pushing harder and harder and harder. I give up. I'm done. And then the object starts moving. But static friction is stubborn because it keeps doing whatever I do until a certain maximum point, and then it quits and lets me win. Now this is opposed to kinetic friction. Sometimes we call it dynamic friction. Sometimes we call it sliding friction because really it rears its head when an object is moving as opposed to when it's at rest. It's the force that resists motion of something that's already moving. Now, that's the car that has its brakes slammed on and it's skidding down the road. It's not nearly as stubborn. Not nearly as stubborn. Because kinetic friction is what it is. If you got a force of 20 newtons kinetic friction, it doesn't matter how hard I push, it doesn't matter how fast the object is moving, the value of kinetic friction will be 20 newtons. It doesn't push harder when I push harder. Right, Liam? Now, let me ask you a question. Just drop your pens again for a second. Let me ask you this question. How many people have ever noticed this phenomenon? You go to push something. Maybe it's the dresser in your room. You want to move the bed over to the other side of the room because you're just tired. It's been that way for the last 10 years. You're tired of looking at it that way. you walk into your room, you want to see something different. So you decide you're going to move your bed over to this side and your dresser over to the other side of the room, and you go to push your dresser, and man, you don't feel like taking the drawers and the clothes out because that would be too much work. So you just start pushing it, and it's so hard to get moving, so hard to push, so hard to push. You push harder and harder and harder, and then all of a sudden it starts moving, and then it slides a bit, and then it's like, oh, it's easier now. Once it's moving, it's easier to move than it is to get it moving in the first place. You ever notice that? Once something's moving, it's easier to keep it moving than it is to get it moving. That's because once something's moving, it's kinetic friction. And kinetic friction is lower than static friction. Not always lower than static friction, but it's always lower than the maximum value of static friction. Remember I said static friction is that pain in the butt, stubborn force that pushes just as hard as it needs to. It's like it's taunting me. I push with 5, it pushes with 5. I push with 15, it pushes with 15. I push with 20, it pushes with 20. Kinetic friction isn't necessarily bigger than what static friction is all the time, but it's bigger than the maximum possible value, or smaller, I should say, than the maximum possible value of static friction. That's why it's easier to keep something moving than it is to get something moving, because kinetic friction is smaller than maximum static friction. I'm going to make a little table on the board here. Let's say that somehow we determine the maximum force of static friction. We'll call it FSF max to be 50 newtons. Now, don't worry about how we get that value. Let's just say for whatever reason, that stubborn, static friction force can push as hard as 50 newtons if it has to. My table is going to have 3 columns. My applied force is how hard I push. The force of the force of friction, static or kinetic, whatever, and then the type of friction, static or kinetic. Let's say that I push with 20 newtons here. Okay, the maximum force of static friction is 50. I push with 20. What happens? Remember, stubborn, static. What happens?
20 newtons of static.
You get 20 newtons of static friction. So applied force is 20 newtons. Force of friction will be 20 newtons, and it will be static friction. It will not move. I push 20 newtons to the right on the desk. Friction pushes 20 newtons to the left on the desk. The net force is 0. It stays where it is. What if I push with 40 newtons? Stubborn, static. I push with 40 newtons. What does friction do? Pushes with, 40 newtons. Stubborn, static. It pushes as hard as I do until it reaches a maximum value. It doesn't move, does it? Because the force is balanced. I push 40 to the right. It pushes 40 to the left. Force is balanced. No net force. Doesn't move anywhere. Pushes the force of 50 newtons. What happens? I push with 50. Hey, remember, it can push as high as 50. So what happens? It does. Does it move? Nope. Therefore, it's static friction. What if I push with 51 newtons? I'm going to push with 51 newtons now. What happens? Stubborn, static.
It'll be kinetic and
It loses. Stubborn, static has finally said, you know what, I'm done with this guy. Okay, he keeps pushing. I try to keep up with him. He pushes with 20, I push with 20. He pushed with 50, I push with 50. Finally, it says, I'm not going to push any harder. Static friction says, I'm done. I'm not pushing any harder. And it just gives up and allows the object to move. Now we've got kinetic friction, because now we've exceeded the maximum possible force of static friction. It begins to move. Now, what's the value of kinetic friction? We don't know. We have to have an equation to determine it, but it's going to be somewhere maybe in the range of let's say 42 newtons. I'm making that number up, but we could calculate it. Bottom line is it's going to be less than 50. Yeah? Yes, but I'm going to pick a specific number here because it's going to show you something on the next one that we do. Yeah, we know it's less than 50. That's all we know for sure right now, but we're just going to make that number up 42. See, you can see the pattern that forms here. Okay, let's say I push on this object with a force of 75 newtons. Does it move? Remember, static friction is already given up, right? Said all I can do is push with 50. He's pushing with 75. I give up. Move. The object moves. We've got kinetic friction. What's the value of kinetic friction? Braden? Yeah, less than 50. Specifically, it would be 42. Remember, it's not stubborn, right? It's not a stubborn force. It is what it is. If kinetic friction is 42, kinetic friction is 42. It doesn't keep, just because I keep pushing harder, kinetic friction doesn't feel the need to push harder in response, like static stubborn does. Let's say I push with a force of 1,000 newtons. Does it move? Of course it does. Stubborn static can only be a maximum of 50. Moves. Therefore, we got kinetic friction. What's the value of kinetic friction? Yep, 42. Or something less than 50, right? Bottom line is these three numbers are going to be the same, regardless of whether it's 42 or 44 or whatever. Yeah.
The harder you push, could the kinetic friction get lower and lower?
No. The harder you push, static friction, stubborn static responds to that. Okay, I push harder, stubborn static pushes harder in response until it reaches the maximum value that it can be. In this case, it was 50 newtons, and then it moves, and we no longer have static friction. Now we have kinetic friction. Now it doesn't matter how hard I push. As long as I push over the maximum value of static friction, then kinetic friction is going to be the same no matter what. I could push with 48,175,212.9 newtons. And the force of kinetic friction would be 42 newtons. This object is moving at 1 meter per second, or the object is moving at 8,000 meters per second. The force of kinetic friction is 42 newtons. Once it's moving, the force of friction will be the same no matter what. As opposed to static, stubborn, which changes depending upon how hard I push until it reaches that maximum. Yep?
What if you push it up?
Okay, that's a good question. What if I push it up? That's assuming that the force that I'm pushing with is parallel to the surface. Yes, that's a good point. If I push it up, then all bets are off now, right? These are all parallel forces. Okay, good question. We'll deal with something like that a bit later on, but we're not ready to go there yet. All right, well, how exactly do we get this number, or this number for that matter? Right, these numbers that we have to calculate. This 20, 40, 50, right? We didn't have to calculate anything there because we knew that the 20 was just equal to the applied force. The 40 was equal to the applied force. The 50 was equal to the applied force. But how did we get that maximum value or the force of kinetic friction? We need a couple equations. The first one, we'll say FSF max. Be careful. This isn't FSF. This isn't the force of static friction. What we're about to calculate is not the 20 or the 40. What we're about to calculate is that number, the maximum force of static friction. The 20 and the 40 just come from how hard I push. The 50 comes from this equation. It's equal to a constant called mu. It's a Greek letter. And it's funny, the Greek letter mu actually kind of looks like an M a little bit, like a handwritten M, but it also kind of looks like a U. It's mu. The Greeks didn't go ahead and name it mu because it looked like RM and RU. Their letters came first. But we can remember it that way. Right? It's mu because it looks like an M, looks like a U. It's just variable that we call the coefficient of static friction. And it's really a measurement of how much two things stick together. It's way easier, if you got a car sitting on ice, it's way easier to push that car and cause it to start moving on ice than it is on pavement, right? The coefficient of kinetic friction between ice and rubber is less than the coefficient of static friction between pavement and rubber. So coefficient of friction is essentially just a value, a measurement of how much two things stick together. The higher the value, the more they stick. The lower the value, the less they stick. So the maximum force of static friction is equal to that constant times the normal force. Now, the normal force for us, for now, will be m times g. I'm going to put a little star by that, though, because it's not always the same as gravity. But for now, it will be. Essentially, whenever an object is, like we are right now, being pushed up on the same as we're being pulled down by gravity, then those two forces are going to be equal to each other. I'll point out to you when the normal force isn't m times g, but it is for now, for the next few days. So remember, this force right here does not get us this value or this value. Okay, the force that we just calculated with this equation gets us this value, the maximum force of static friction, which we're going to use to compare in this table. Now the other equation is the force of kinetic friction. Notice, by the way, these two vertical lines, what does that mean? Right?
It's an absolute value.
It's an absolute value. So it means that whatever we get, it's a positive value. Okay, we're never going to get a negative value from this equation. Force of kinetic friction is equal to mu times Fn. Remember, that's not the stubborn force. So whatever we get here is not the maximum possible value. The value that we get when we use the red equation there is this, or 42 newtons. Doesn't matter how fast it's going, doesn't matter how hard I push, the force of kinetic friction will always be 42 newtons if mu times Fn equals 42. Here's a table for you that you're going to be given when necessary. Just gives you values of static friction coefficients and kinetic friction coefficients. What you notice is that static friction is bigger than kinetic friction, right? The coefficient, that is bigger. Copper on copper, so if you have a copper box sliding on a copper plate, it's a pretty big coefficient of friction. So there's going to be a big resistive force there, whether it's static or kinetic. Take a look down here. Rubber tire on dry asphalt, right here. 1.2 and 0.8. Rubber tire on wet asphalt. How many people drive? Sometimes you notice you skid more on wet pavement than you do on dry pavement. It's because the coefficient of friction is a lot lower on wet pavement than it is on dry pavement. How about rubber tire on ice? That's way, way lower. That's why you skid way easier on ice than you do on dry pavement or wet pavement. How many people have winter tires on their vehicle? Okay, it's a good thing. When I was younger, we had all-season tires. And we still put all-season tires on now, but we usually try to limit them to the summertime because they're not really all-season in Alberta. What happens to those all-season tires when it gets cold, the rubber gets a little bit brittle. It doesn't stick very well to the road when it's cold. Winter tires are made with a different rubber formulation. Below 7 degrees Celsius, it gets a little softer and sticks to the road better. So winter tires, it's not the tread in winter tires that's the good thing that provides the traction. It's the rubber compound. The rubber compound in winter tires has a fairly significantly higher coefficient of friction between rubber and ice than does than does the regular rubber that we use in all-season tires. So if you don't have winter tires, you should get them because it's way better in the wintertime. Not because, as I said, the tread is almost irrelevant. Okay, what's important is the coefficient of friction. It's way bigger. If you go way down here, synovial fluid. Anybody know what that means? Synovial fluid? Today?
It's the fluid that surrounds the joint to reduce friction.
Yeah. And look how low that is, right? The fluid that is in your joints to reduce friction. Like 0.01. Like it lubricates your joints. And listen, it's a good thing that you have this incredibly low coefficient lubricant in your joints. Otherwise, when you did this with your arm, with your elbow, it would be squeak, squeak, and then it would hurt a lot, right? If it was bone rubbing on bone. Can you imagine how much that would hurt? So it's incredibly low coefficient of friction. Now, notice that static and kinetic are the same. They're not really. If we kept going to more significant figures, kinetic would be slightly less than static, but not much. It's almost the same in that case. Almost the same. Do you guys notice a difference, by the way, when you go to start moving your joint versus your joint is already moving? I don't. Right? And that's because static friction coefficient is pretty much the same as kinetic friction coefficient. Make sense? Okay. Let's take a look at an example from chapter 3 in the textbook, page 185. It says a sled with waxed hickory runners rests on a horizontal, dry, snowy surface. Waxed hickory runners, dry, snowy surface. Calculate the mass of the sled if the maximum force that can be applied before it starts moving is 46 newtons. What are they giving me there? 46 newtons. The maximum force that I can apply before it begins to move. Here's my desk. Push with 5 newtons, nothing happens. 10 newtons, nothing happens. 15, 20, 45, 50, nothing happens. 51, desk moves. What was the maximum force that I could push with before it began to move? 50. That was the max force of static friction, right? That's what we got here. The max force before it will begin moving is 46. My maximum force of static friction is equal to how hard I can push before it begins to move. Now, that doesn't mean static friction is always 46. Maybe it's 20. If I pushed with 20, that's what it would be. If I pushed with 40, that's what static friction would be. If I pushed with 46, static friction would be 46. If I pushed with 47, it moves and it's kinetic. The coefficient of static friction, by the way, waxed hickory runners, dry, snowy surface. Waxed hickory, dry snow, static, 0.06. No units, by the way, for that. Just a number. What do we say Fn equals to, at least for now, for us? Yeah? Yeah, it's gravity, right? M times G. Or you could say M times A if you recognize that A is 9.81. So what do we got here? 46 divided by 0.06 times 9.81. We dropped the sign of the 9.81 here because we're dealing with magnitudes. Let's get this here. Let's say 46 divided by brackets 0.06 times 9.81. 78 newtons, or 78 kilograms. Doesn't move, right? I'm pushing it hard as I can push it before it begins to move, 46 newtons. It's not just static friction, it's the maximum static friction force, which is always the number we use in the equation. Where's my mistake here? Just a little thing that I missed. Yeah. Yeah, it should actually be how many digits? 1 digit. So it should be 8 times 10 to the 1. That's kind of ugly, actually. I don't like it when they make it one significant digit like that, but it is what it is. All right, let's have a look at questions 1 and 2, page 185. Tables up there for you. Remember, question like number 1. An applied force of 24 newtons causes it to start moving. Essentially, we're saying, look, you apply 24 newtons before it begins to move. What is that?
Static force max.
Yeah, that's static force max, right? Question 2 is a little bit different. Are you applying a force of 125, like when it starts moving? No, it's saying, would it move at 125? Yeah, it's a little bit different. We're going to get you to think about that one, and then we'll come back in a few minutes to take a look at both of them. All right, have a look up here. Question number 2 asks us, would the sled move? It's different than question number 1, because question number 1 says, look, I can push with 24 newtons before it begins to move. I push with 20, nothing happens. 21, nothing happens. 22, nothing happens. 23, nothing happens. I can push with 24 before it begins to move. That means that's the maximum force of static friction. We don't know the maximum force of static friction number 2. We just know that we're pushing with 125. Does it begin to move at 125? We don't know. We're not told this. So what we got to do in question 2 is find the maximum force of static friction. We do that by multiplying the coefficient of static friction by the normal force, which is waxed hickory on dry snow, 0.20, times m times g. I think it was 78.1515 times 9.81. That gave me a value, I believe, of 150, wasn't it? What is it? 153? Or 1.5 times 10 to the 2. Now, I push with 125. Maximum static is 153. Stubborn static. Remember, it can do whatever I do until it reaches its maximum value. Have I reached its maximum value? I pushed with 125. Maximum is 153. Have I reached its maximum value? Nope. Who wins? Who wins? Stubborn static or me? Static friction wins because I haven't pushed hard enough to exceed its maximum. I need to push with 153.1 to exceed its maximum. So does it move? Nope. Because the force of static friction is greater than the maximum force of static friction is greater than the applied force. Okay, let's do one more example. And then that's all the examples I want to do with you today. This is a little bit different, easier. I think you're going to find this one easier. This is a 1640 kilogram lift truck with rubber tires is skidding on wet concrete. Hey, skidding, what does that mean? It's moving, right? It's sliding. Remember we said kinetic, dynamic, sliding friction? Skidding on wet concrete with all 4 wheels locked. What's the acceleration of the truck? We're going to say force of kinetic friction is equal to mu times the normal force. Or the force of kinetic friction is equal to, what do we get? Rubber tires, wet concrete. Rubber tires, wet concrete. Kinetic friction, 0.5. M times G, 1640 times 9.81. Here's my force of kinetic friction. $8,044.2. Now what? That's the easy part.
Then you use the acceleration you learned.
Yeah. Yeah, the one you learned the other day is equal to F over M. we're going to say 8044.2 divided by the mass of 1640. So it's equal to 4.905 meters per second squared, which we're actually going to round to one digit because of this again. 5 meters per second squared. Now, strictly speaking, when we calculate this 8,044, it's absolute value, right? When we sub it into here, it should actually include a negative direction because it's opposite to the motion. But I wouldn't take any marks off if you missed that. Okay, that's a tiny, tiny little thing. Really what we did first is found the magnitude of the acceleration, not the actual acceleration, but that's good enough for this question.